So, time is 8 p.m. GMT.
Hello, everyone.
Very confusing to calculate the offset, I guess. But I think it's the best time for most of the continents. So let me officially start this webinar series by saying a very warm welcome to all the participants. And I'm extremely happy to host this series of events. So to those of you who didn't meet me previously, so my name is Evgeny Osipov. I'm professor at Luleå University of Technology. Luleå is a cozy town, well, small but cozy town in the northern Sweden. And the motto of our university is that great ideas grow better below zero. Well, yeah. That's just to tell an early joke for for Melbourne. Nevertheless, this is the first event of a series of webinars on vector symbolic architectures and hyperdimensional computing. So I would say a long-awaited event. The hope was to meet with many of you personally in Heidelberg early this year, but circumstances didn't allow us. So we decided why not to meet online. So, and I'm very happy to see that already now we have 31, 32, maybe soon 33 participants. So without any due delay, so I leave the floor to Rose Gayler. So we have two talks today, one by Rose, one by Hedda Schmidtke. So a little bit about procedure. So I will be moderating the session. This means that if you have any questions, so please type them into chat, and we will take them after the end of each talk. So you should count that the whole event will take approximately 1 hour, so around 25 minutes per presenter. So Rose, please. The floor is yours. And please, all others, please mute your microphones, except for those presenting. So you may leave your video on, so that's okay, but please be sure that your microphone is muted. Right, and also I want to, the last warning is that I'm recording this session so that it will be available offline. Right. Okay, I'm muting myself. Rose, please, the floor is yours.
Okay, thank you very much, Evgeny. Good morning to everybody from Melbourne in Australia. Not quite dawn yet here, but we're working on it. I'll move into this, I should say thank you very much to Evgeny and the other organizers for putting all this together, and just echo his thoughts that it's great to see you all and finally get on to this. Now, if you'll give me a second to just reorganize myself here, I'll share my screen and make one more change that you can't see. Okay, back to business. Right, this talk is not a presentation of any new material. It's basically me trying to sell an idea which I think is very important, which I've been working on for quite a long time, but I think it would be very valuable if more people would be looking at it. So obviously it's bound up with the essay hyperdimensional commuting, but also analogy, which is my primary motivation. And I think the idea which I'd like people to take away is one of dynamic similarity. So we'll go through that. I'll start off just by motivating the problem. I came into this sort of basically as an old school AI person. So I'm interested in, what is it necessary to allow us to create the equivalent of human scale intelligence artificially. And so obviously this is interested in questions of analogy, of cognition. Excuse me, I just need to organize one more thing here. Sorry, I'm just going to disappear for a second. While that's better. Sorry. Okay, back to the talk again. So there is an argument that analogy is at the core of cognition, that essentially if you want to attain human level performance, you need to be able to do analogy. And in the analogy literature, that's commonly construed as a problem of structure mapping between a source and a target structure. So essentially it's saying that if you are able to structure your knowledge of the current situation of the world as graphs, then what you're looking for are to find maximal subgraph isomorphisms between these source and target graphs. So the notion is that you have graphs which have different labels on them, but you're looking to find some way of aligning them so that there's a maximal correspondence between the elements of those two graphs. And the point is, in doing that, another way of saying that is you're finding a mapping between the labels on the nodes of one graph and the other, such that if you perform that substitution, that mapping of labels, then to the greatest extent possible, you can turn the one graph into the other. So you make them identical or close to identical. Now, that feeds into notions of similarity and generalization, which is more general to machine learning and cognition in general, that if you consider the task, the evolutionary task of some agent acting out in the world, they need to be able to generalize as widely and as rapidly as possible. So those of you who are old enough might remember the early days of neural networks when backpropagation was a big thing. And one of the arguments about that was that it just took an awful lot of effort, computational effort, to get a system to the point where it could generalize even mildly well. But if you look at some of the critiques around deep learning these days, you'll still see that there's a concern that artificial neural networks don't generalize as widely as humans are capable of generalizing. So it's an important goal to aim for. And generalization usually either invokes or even induces a concept of similarity. So the notion is that if you're generalizing from one situation to another, that in some sense that's functionally meaningful to that device, there's a similarity between those situations. And typical statistical and machine learning models use literal similarity. The similarity is defined in terms of literal values which are there present in the stimulus. You know, the value of some specific pixel is high or low, and it has to be the same in every other situation which is regarded as being similar to this. Now, obviously, we're getting away from that with some aspects of deep neural nets. Again, it's getting into more relational things, but what we're trying to do with analogical similarity is to put relational similarity front and center. So relational similarity is encoding relationships between the literal values present in the stimulus. And analogical similarity can be seen as taking that even further, that it's based on relational structure, so relations between relations in the stimulus, or higher order relations, if you like. Now, the next couple of points there, I've got question marks again because these are somewhat more speculative. But I think that one of the reasons this is important is because I think that relational structures tend to reflect real causes in the environment. If you think from the point of view of some visual creature, that as its point of view shifts, some particular point of significance is going to move all around across its field of vision. Whereas if there are causal things going on in the world, then they're likely to induce relationships between pixels in its visual field, and those pixels may move around, but the relationship is still constant. It's just constant with respect to literals that are moving within the visual field. Another thing that I think is important about analogical similarity is that it may reduce the reliance on good encoding of literals. We'll come back to this encoding issue a little bit further on. But you might recall, if I go back a slide here you can see some of the labels: planet here, electron here, sun here, nucleus there. Those labels are different between the two graphs, although some of these other labels, and all the other labels in fact, are the same. But in principle, if you're talking about graph isomorphism, the labels are not necessarily relevant at all. It's only the patterns of edges which are relevant. So whereas in, oops, sorry, wrong way, in standard machine learning, often half the problem is finding a good encoding of the literal values. That if what you're interested in are the patterns of relationship, and it really doesn't matter what are the labels on the nodes, then presumably you're reducing the reliance of the learning system on finding good encodings. Another thing to bear in mind is that literal similarity, which, as I've been saying, is what standard statistical and machine learning models tend to deal with, can just be seen as a special case of analogy. So if we're thinking in terms of these mappings of labels from nodes on one graph to another, literal similarity is essentially just saying, well, it's an identity mapping from one graph to the other, so it's a special case. So we're not losing anything. Now, in VSA's hyperdimensional computing, similarity is a core concept. It's really central to the way these systems operate. And the way this is normally conceived in this field is as a static similarity, which I'll get through to explaining. But it's a central concept, and the similarity is taken as being the angles between the vectors representing certain states or objects that we're interested in. And typically in doing this work, there's a fixed mapping from things to vectors, from things to their representations in the VSA space. And so that then means that there's an emphasis on finding encodings that yield a useful similarity structure. So usually the experimenter has in mind that certain things ought to be similar to each other in order for the agent to do what it needs to be able to do in this space. So then the experimenter goes to a great deal of effort to find some way of encoding those entities into the VSA space, so that the vectors of things that the experimenter believes to be similar actually do have non-zero similarity as dot products within that space. Now, you could either engineer those in directly, but sometimes the relationships, those representations may be learned using things like random indexing or vector embedding and so on. But the point is that although you may be learning those representations at the point of use, these are effectively fixed. And so the similarity structure, the set of similarity relationships between all the things you're representing are fixed and static at the time of use. Now, going back to humans for a bit, in humans, it's reasonably believed that human similarity judgments are context dependent. Another way of saying that is that a static similarity structure doesn't capture what it is that humans do. So if you say, what's the similarity between Australia, New Zealand, the UK, and so on, you get judgments on that. That will differ. The similarity structure you'll get will differ if you were embedding that in a different set of other countries, Sweden, Austria, and so on. So it appears that humans are able to change the similarity structure on the fly. And it's been argued that the same processes underlie both analogy and similarity judgments. Now, the next point is really quite interesting. It's been argued that representations are actually created on the fly in response to task demands. So this paper by Chalmers, French, and Hofstadter is well worth reading. It was a reaction to artificial intelligence standard practice at the time. So people tended to have a separate perception module and a separate cognition module or reasoning module. And so the notion was that perception would look at the world and would create these representations and would then be handed across to reasoning to do things with. So the representations were created without reference to how they were going to be used. And so it was almost as though there was a canonical representation for everything which might exist in the world, and this would support everything you needed to do to reason and work with them. But these people were arguing that it actually made more sense to think of the representation being made in response to the task demands. So, for example, if you had a bottle, if you were interested in drinking, then the representation might be in terms of the contents of it. If you had a window that you wanted to keep propped open, your representation of the bottle might be more in terms of the fact that it's solid and it has a vertical extent that can be used to wedge the window open. If you were in an argument with somebody, it might be represented more in terms of being a heavy object that you can hit them with, and so on. So it's quite an interesting concept. Now, if you do accept that, that doesn't necessarily imply that there isn't some sort of a base core representation which is relatively static. I mean, if everything was completely context dependent from the ground up, that would seem hard to implement. But I think it's relatively straightforward to think that there could be, if you like, a working representation of the objects which are currently in play, and that working representation could be derived from some relatively static base representation by a context-dependent transformation. And so that context-dependent transformation would be where the information about the current situation comes into play and molds the working representation to suit what you're going to do with it. So getting back to VSAs now, it seems to me that an obvious candidate for a dynamic transformation function is substitution by binding. If you're not familiar with it, if you have, for example, a binding of some arbitrary vector A with another vector which is the inverse of B, that binding can be considered a substitution operator. If you then bind that composite with some other binding which contains a B, the inverse of B cancels out the B, and the A gets grafted on. So the effect is to take B's in the target structure and replace them with A's. So that substitution will work systematically over an entire representation, a complex structural representation. So the point about those is you can represent substitution mappings in a VSA system, and they can be specified as a vector, and they can be dynamically generated. So you can create these things on a fly. Now, if you've got a VSA system that's doing that, and that's central to the operation of the system, that implies some architectural features about your VSA circuit. There needs to be an internal degree of freedom, a register, if you like, to hold the value of that substitution vector while it evolves over the course of the computation. And I think there needs to be a recurrent VSA circuit to provide the dynamics to evolve the substitution vector. I mean, obviously there's got to be some sort of dynamics to create it, but I think it needs to be recurrent, because if it's not recurrent, then effectively you're saying this value can be created in a single step, which then effectively gets you back to the position of saying, well, actually, everything I need to know has already been encoded into the values. I can just automatically derive in a single step whatever I want from the values. So it seems to me to be getting back to effectively a static situation, which I think for human level cognition, it won't be possible to have a static similarity structure which can do everything you want. So to give an example of a circuit like this is some work I did quite some while ago with Simon Levy. And we developed a VSA circuit which found, for very small graphs, a maximal subgraph isomorphism between two graphs. So we'd take two graphs, represent them as vectors, feed them into this circuit, and the circuit would then settle to a state which represented the mapping between the vertices of the two graphs. such that that mapping corresponded to a maximal subgraph isomorphism. So perhaps if we look at the graph down here on the bottom, each of these curves represents the degree of belief in, degree of presence of a mapping between vertices. The two graphs had vertices labeled A, B, C, and D on the one part, and P, Q, R, and S in the other graph. And so you can see that the AP mapping goes up, stays high, the BQ mapping goes up and stays high, etc. So these curves over here correspond to the vertex mappings, which give the desired result, and these other curves here represent to the vertex mappings, which are not part of the solution. So you can see that in terms of a discrete iterative circuit, this thing has settled by about 20 iterations. And what's happening here is this x sub t is a vector representing the degree of belief in each of the possible mappings between the vertices of the two graphs. And that's evolving over the course. So you can see it's going down into here. It's being multiplied by this vector, which represents what's basically the product of the two graphs. So that's a constant. These things here are constants. This vector represents the it's called the payoff, but essentially it's a Bayesian update vector representing the degree to which those beliefs should be updated. This is an intersection operator. All this is done with VSA circuits, so it's intersecting. So this is basically applying a Bayesian update of our prior beliefs and the weight of evidence, and then we've got the inevitable cleanup operation and a bit of rescaling just to stop the values exploding. So ask me about that sometime if you like, and I'll go through that in detail. But anyway, I think that subgraph isomorphism circuit can be seen as related to recent developments. So the resonator circuits for factorization that the people at Redwood Center developed just last year. That's a very interesting circuit. It takes a binding of a number of different vectors and recovers the items that have been bound together. And it does that in terms of being able to recreate the binding from the unbound components. So it has internal degrees of freedom, which represent each of the factors to be calculated, and it has a recurrent VSA dynamics that settles on that factorization. A couple of other ways of viewing that same circuit. If you like, you can think of it as being effectively finding the geometric mean of the two graphs which have been presented to it. It does actually explicitly in the construction of the circuit, it creates a data structure which represents the structural product of the two graphs. And effectively the subgraph isomorphism is the mean of the two graphs. It's sort of the graph which is closest to both of the source and the target graph. Or another way to think of that circuit is it's finding a factor, which in this case is the substitution vector, such that the product of that factor with each of the graphs is a good approximation to the other graph. And that's quite a nice way of thinking of it, because that then links that back into statistical modeling, where factorization of complex data is fairly standard. If you think of principal components analysis, if you think of factor analysis or tensor factorization, there's a long history in statistics of trying to approximate some complex structure as a composite of factors which can be put together to approximate that. Finally, just looking at the kind of work which can be done along here, at the moment, that circuit only takes two graphs, whereas if you're trying to build a proper cognitive system, you'd want an analogical memory where you're taking a query graph and you have a memory that's stocked with many thousands, millions of other graphs, and you've simultaneously got to find the match, the substitution which gives the best match out of all those graphs and returns that graph. There are also extensions possible to hypergraphs rather than graphs, so rather than just binary edges with a higher order, There's some cognitive arguments about why that might be interesting. And finally, that there are still within these systems some problems. Some cleanup memories may have localist representations, whereas it would be good to have the entire thing being thoroughly distributed. So no localist representations anywhere. And that's it. I've put this stuff up on the web if anybody wants to find that. And there's also a reasonable list of those references there. Evgeny.
All right. Thank you, Ross, for your presentation. So now we are open for questions. So I guess those of you who have questions to Ross, please unmute yourself. So I don't see any questions in the chat. Please use the microphone.
Yeah, Ross, I have a question here. Fritz, let me switch on the video. Yeah.
Hey, Fritz.
I'm just wondering, how good are humans really at this graph isomorphism problem? I'm just wondering. I mean.
Okay. Yeah.
Yeah.
So humans are probably absolutely rubbish at graph isomorphism, in the same sense as humans are rubbish at doing maths and arithmetic and so on. It's a very slow process to do explicitly. So it's more that graph isomorphism is the standard mathematical model that theorists go to when they're trying to explain what's happening in analogy.
Yeah. Okay.
So it's a completely automatic process, is the notion, and really it just falls out of the fact that if you're looking at a complex structure, then you're trying to find some degree of equivalence between complex structures, especially where you've got networks of propositions which are referring to the same literals. Then it's sort of the natural representation.
Yeah.
Right. Any more questions to Ross? Okay. Thank you, Ross, once again. So I